Hi, welcome back. We are now doing the next aspect of it. This is called the stretch tensor, and it is simplification for almost rigid bodies. Okay, so off we go. The computation of the dot products can be simplified into matrix operation. What do I mean by the dot products? If you remember last time, we were trying to find this S1 and S2 and all of this stuff. We need to be able to do that in a more effective way. If you compute F transpose F and use its column vectors Fi for F, you will get all possible dot vectors between dot products between the column vectors. What do I mean is F transpose F is just this. F1 dotted with F1, F1 dotted with F2, F1 dotted with F2, F2 dotted with F2. So it's column vectors of F dotted with each other is what F transpose F does. Okay. So F1 dotted with F1 we know is S1 squared. F1 dotted with S2 is S2 squared. And then F1 dotted with S2, F2 is S1 S2 cos theta. And the other one is also S1 S2 cos theta. So you can see that if I know F transpose F, all the information about lengths and angles are there. This is a very important result. So please memorize this particular structure and memorize it in words. The local stretch area ratios and angles can be read off from the matrix formed by F transpose F. The diagonal terms gives the square of the stretch ratios among the axes. Can you see S1 squared and S2 squared? And the off diagonal terms can be used to find the angles because it was S1, S2 cos theta 1, 2. So once I know S1 and S2, I can find out cos theta. That's how it works. The symmetric matrix formed from F transpose F should be called the squared stretch matrix. But unfortunately, that's not the name that would have been useful to remember. It's called the Cauchy Green matrix or the Cauchy Green Stretch tensor, and its symbol is C for Cauchy. We can simplify the calculation for almost rigid bodies. Why do we need to simplify? Because I want to show you one thing. This one is okay. This is just a polynomial S squared. This one has this cos theta 1, 2. This is a headache because it's a cosine function. We don't like it. Right? We want to simplify that. But it cannot be done in general. But for small deformations, we can. So we're going to look at the calculation for almost rigid bodies. We have written the squared stretch matrix as F transpose F, but we want it in terms of the gradient of the displacement H. So what we do is we substitute F equal to I plus H. When you do that, you will get C equal to I plus H transpose H. So can you see that there is a constant term, which is I, there's a linear term H plus H transpose, and then there is a quadratic term H transpose H. So if H is very small, which means that the current shape is very, very close to the starting shape. I made a typo there. It's not same. It should be shape. Okay. Then we can throw away the square terms and get a simplified version. C is approximately I plus H transpose. We are keeping only up to linear terms. We throw away the rest. For small deformations, I plus H transpose approximates the stretch ratios and the included angles in a nice way. We will see this now. So the approximation has specific meaning for almost rigid bodies. What do we mean by that? Remember that C was S1 squared, S1 S2 cos theta 1, 2, S1 S2 cos theta 1, 2, S2 squared, which is I plus H transpose. So it took a rectangular thing and slightly deformed it into something that's not quite rectangle and it's not quite the original length. It's slightly changed, right? So you can see that to get the meaning of this approximation, we will see what happens to the stretch ratios and angles for almost rigid bodies. So what will happen is S1, which is the stretch ratio, final length or initial length, will be very close to 1 because it's not extending much. So let us say it is 1 plus E11. So it's slightly more than 1. So it's E11 more than 1. And E11 dx is the extension of the line element, how much it is pulled. So since S1 is very close to 1, S1 squared is 1 plus 2E1 plus E1 squared. And we are throwing away this E1 squared, quadratic term we are throwing away. So that is why I get 1 plus 2 E1. I can do the same thing with S2, and you can see that picture there. S2 is 1 plus 2 E22. So it does not giving me 1 plus E11. You can see that it gives me this pesky 2, and that we'll have to take care of. We will think about that later. Okay, the angle is very close to 90 degrees. So we'll say it's a little bit less than 90 degrees, say pi over 2 minus gamma 1 2. This gamma 1 2 is the angle that is away from 90 degrees. Think of it that way. How much less is it from 90 degrees? So cos theta 1 2 is cos pi over 2 minus gamma 1 2, which is sine gamma 1 2. Okay, that's nice. But now we know that gamma 1 2 is small because the angle will be almost right angle because it's almost rigid, right? So what will happen is that sine gamma 1 2 will become approximately gamma 1 2. So now I have a very nice result. S1 S2 cos theta 1 2 is 1 plus 2 E1 times 1 plus 2 E2 times gamma 1 2, which is approximately gamma 1 2 if I throw away all higher order terms other than the linear small terms. Okay, E1 times gamma 1 2, E1, E2, gamma 1 2, all of those things are too small. So we'll throw them all away. We are left with only this much. So C will approximately become 1 plus 2 E1 1, gamma 1 2, gamma 1 2, 1 plus 2 E2. And this is what is there in 1 plus H transpose. Right? By subtracting identity from both sides and dividing by 2, we get what is called the small strain matrix. Looks like E1, gamma 1 2 over 2, gamma 1 2 over 2, E2 is 1/2 of H plus H transpose. And this is what is usually written as E11, E12, E12, E22. In this particular exposition, I have taken you from the large deformation and showed you how to get the small deformation. The large deformation calculations are exact. That the first part of C12 with the S1 squared, S1, S2 cos theta 1 2 is exact. Then I showed you how you get the small version. In your undergraduate textbooks, they will try to directly derive this by making simultaneous assumptions and all of that. That's a mess. This is very clean and it's super simple. Okay, so this is what we are going to use. The symmetric part of the displacement gradient approximates the changes in local lengths and angles. The diagonal elements approximates the change in length of the axial line elements, and the off diagonal components approximates the change in angle. These are not exact. These are approximate. The exact version is there in the C matrix, S1 squared and S1, S2 cos theta 1 2 and so on. With that, we are done. Thank you.